Let's do a little bit of work on potential now, and we'll group it together so that we do an example of finding the potential in the region of a group of charges. We'll lead that into finding the potential due to a continuous charge distribution, and then we'll calculate the potential if instead of this being a set of discrete charges, it was actually a line of charge. Okay, let's start by saying we have 7 charges on a line. They each have an equal charge of 1.25 nanocoulombs, and they're each separated by 1 millimeter. So every distance here is 1 millimeter. So the total separation between all of the charges then would be 6 millimeters. We'd like to find the net potential, electric potential V or voltage, at a point P, which is a half a millimeter from charge Q4. I'm going to call this distance, since it's horizontal, X, and I'm going to write down that that's a half of a millimeter. Okay, I'm trying to find the potential right here. So we know that the potential due to a single point charge is K times Q over R. Two differences between potential and electric field. Electric field is KQ over R squared, and electric field is a scalar. And electric field is a vector. Potential is KQ over R, and potential is a scalar. Okay, that means no direction. If we have a set of charges, then the net potential would be the sum of each individual potential, or each KQ over R added up. Okay, so we have 7 charges here. We're going to find 7 potentials and add them up. So let's start with the first one. So Q1 is a distance R1 from our point P. I'm going to label that R1. R1 is equal to the square root of x squared plus y squared, 0.5 millimeters squared, plus 3 millimeters squared, equals 3.0414. Q1 is equal to 1.25 nanocoulombs, which we might call Q. And a nanocoulomb is times 10 to the minus 9 coulombs. So our first potential, V1, is K times Q1 over R1. Put that through the calculator, 3,695 volts. Notice no direction or anything, it's just a number with units because it's a scalar. Okay, next let's find V2. So Q2 is a distance R2 from our point. R2 is the square root of 0.5 millimeters squared plus this distance squared, which is 2 millimeters. I'm sacrificing some sig figs here for the sake of space on my page. 2.0616 millimeters, which is 10 to the minus 3 meters. Q2 is our same charge Q. V2 is KQ2 over R2. So V2 is 5,451 volts. Probably you get the idea what we're doing here now. Let's do Q3 next. It's a distance R3 away. R3 is the square root of a half a millimeter squared plus 1 millimeter squared. That distance is 1.1180 millimeters. Q3 is the same charge Q. V3 is KQ3 over R3. So that potential 3 is 10,051 volts. You see that our potential gets bigger as the charge gets closer. That makes sense because V is KQ over R. If we're closer to a charge, the potential due to it is bigger. Our fourth potential is due to charge 4. So R4 is equal to X is equal to 1/2 of a millimeter. Q4 equals Q. V4 is KQ4 over R4. And that potential is 22,475 volts. Charge 4 is the closest, it has the biggest potential. Okay, next we get down to Q5. So Q5 is a distance R5 away. We see that R5 and R3 are the same. Q5 is our same charge Q. That means that V5 is the same as V3, 10,051 volts. Next we have Q6. It's a distance R6 away. R6 is 0.5 squared plus 2 squared. It's the same as R2. Q6 is our same charge, so V6 is the same as V2, which was 5,451 volts. And then last we have Q7, which is a distance R7 away. R7 and R1 are the same. Q7 is the same charge, so V7 is the same as V1, 3,695 volts. Our net potential then, due to all of these charges, is equal to the sum of all these numbers. So V total is the sum of every potential. Do that in the calculator, we should get 60,869 volts. And if you wanted to round that off to 3 sig figs, V total equals 6.09 times 10 to the 4 volts. Okay, there's our potential due to our 7 charges. Okay, let's build to the idea of a continuous distribution of charge. We're going to use the same concepts that we used when we built the idea of an electric field due to a continuous distribution of charge. On this side of our slide here is a summary of what we just did. The net potential at any point is the potential KQ over R due to each point added up. So the next step in building a continuous charge distribution is that we squeeze the charges together. So that's an intermediate step. We start to take these charges and we pull them all together. The next thing that we do is we make each charge very small. So we have a whole lot of tiny charges. When we make each charge small, what happens is that each individual charge Q goes to a little bit of charge that we call dQ. The potential due to each charge goes to a little bit of potential, and the sum of all of our potentials goes to an integral of all of our potentials. So to find the potential due to a continuous distribution of charge, so this is our continuous distribution, so this is our group of very small charges, all very close together. Our net potential is going to be the integral of dV, which means we're adding up each small bit of potential made by each small bit of charge. So our net potential is the integral, or the sum, of each small bit of potential. And each small bit of potential is given by K times each small bit of charge divided by the distance between the charge and the point. So this is the idea. You've probably done this in Physics 1051. I'm going to go ahead and do the example of a long rod. It will be a review for most of you, but maybe it'll be useful. And then what I'm going to do is first we'll find the expression, and then we'll put in the numbers so that it has the same amount of charge and the same size as this distribution, but it'll be a continuous distribution instead. We'll see how those answers are different if we become a continuous charge distribution. So let's say we have a rod with a length of 6 millimeters. It has a net charge of 8.75 nanocoulombs, uniformly distributed along its length. We want to find the potential at point P, which is a 0.5 millimeter from the midpoint of the rod. Okay, let's get some labels in there. This is our distance x. That's 1/2 of a millimeter. I'm going to put in a coordinate system. I'm going to put my origin right through the center of the rod. My x is horizontal. My y is vertical. We start these problems the same way we start our electric field problems. You identify one small bit of charge on your continuous charge distribution. In electric fields, we make a big deal about the symmetry. Electric potential is different. There's not really any symmetry to talk about because there's no direction. So you got to be really careful when you think about potential and remember that it's a scalar. So this is our small bit of charge. Label that dq. The distance between dq and our point P is what we call r. On our picture, this is a hypotenuse of a right-angled triangle, and this leg of the triangle is from here to here. That's our y-coordinate. We might notice here that x is constant. You don't have to write this in your picture, but if you're trying to set up the integral and you feel like you need a little bit of help, this is a good way to keep all your ideas straight. And your y is a variable. So ultimately, since y is variable, we know we'll integrate with respect to y. The total length of our rod from here to here is 6 millimeters. I don't have a lot of room in my picture, but I'll try and get it in there. So this is L, 6 millimeters. Okay, let's get started. We know that our net potential V is the sum of each little bit of potential dV. Let's write down what dV is. dV is the little bit of potential made by charge dq. dV is k times dq over r. So we can fill that bit in. Next, let's deal with dq and r. dq is the amount of charge on this line of charge. So dq is going to be the charge density lambda times the length of our little element of charge. The length of our little element of charge is a little bit in the y direction. It has length dy. Now I've written down lambda, but it's not given in the problem, so I should write down what I mean by lambda. Lambda is the net charge over the net length. So this is our net charge q. This is our net length, 6 millimeters L. If you wish, you can go ahead and calculate that here. I think I won't just yet, but you certainly could if you wanted to. So this is our linear charge density. And so that takes care of dq. We also need r. R is the hypotenuse, so r squared is x squared plus y squared, or r is the square root of x squared plus y squared. Okay, let's put these things in our expression. Equals the integral of k times lambda times dy over the square root of x squared plus y squared. You might notice here that I didn't talk about sine and cosine. I didn't label an angle. It's because my potential is a scalar and I don't have to put in components. I know I'm kind of stressing that a bit, but some people always tend to find it a little bit confusing. Feel free to zone out whenever I discuss it if you're happy with that concept. I'm going to take my constants out front of the integral. K is a constant and lambda is a constant. So I've got dy over x squared plus y squared. Here's a good place to put in the limits of my integral. I'm finding the potential due to the rod, so I need to integrate over the length of the rod. I'll go from the bottom to the top, so minus L over 2 to plus L over 2. Just like with electric field, if you don't choose your limits correctly, you might get a funky sign at the end, so you should always stop and take stock. When I look at this charged rod, I see that the charge is positive. I know that my potential is going to be positive. So even if I end up with a negative sign here, I know in the end my potential has to be positive. You should always let your common sense prevail over math. Okay, so I'm going from the bottom of the rod to the top of the rod. This integral you can either do on your own or you can look up in a table of integrals. I'll choose to look it up. So our integral is k times lambda times the natural log of y plus the square root of x squared plus y squared That's got to be evaluated at our limits of L over 2 and minus L over 2. That gives me k times lambda outside of natural log y is L over 2 plus square root of x squared. Y squared is L squared over 2 squared, L squared over 4, minus natural log of minus L over 2 plus square root of x squared plus minus L over 2 squared is still L squared over 4. What will I do next? I see here that I'm subtracting two logarithms. So here I'll remember the function that log A minus log B, and this is true for natural logs as well, equals log of A over B. So I can divide those two arguments, k times lambda, outside of natural log of L over 2 plus square root x squared plus L squared over 4 divided by minus L over 2 plus square root of x squared plus L squared over 4. Now, if you wish, you can probably simplify this a little bit. As far as I'm concerned, this is okay. This is more or less workable at this point. Let's put in a reminder of what our numbers are. So this is the expression for potential, a distance x from the midpoint of a rod with length L that carries charge Q distributed over its length. I'm going to put in that my L is 6 millimeters, 6 times 10 to the minus 3 meters. My net charge is the same net charge I had in my previous system, which is 7 times 1.25 nanocoulombs, 8.75 times 10 to the minus 9 coulombs. What else do I have? My distance x is a half a millimeter from that midpoint, so 0.5 times 10 to the minus 3 meters. I can put all those numbers in there, and then what I get from my potential is 65,322 volts. And if you wish, you can write that with 3 significant digits. 6.53 times 10 to the 4 volts. So let's just take a quick look at what we had when they were discrete charges. When they were discrete charges, it was 6.05 times 10 to the 4 volts. When it's a line of charge, it's 6.53. They're in the same ballpark, but you don't get the same answer. So the nature of the charge distribution really matters. Set of charges distributed this way doesn't give exactly the same potential as a set of charges distributed this way. And that kind of makes sense because the position of each charge matters. And these guys, it's just not the same as the position of these guys. So we get a similar result, but not the same result.